and welcome to The Most Significant Bit, a podcast that explores the connections between engineering, technology, humanities, and the arts. I'm Griffin Packwood, and I am a MFET engineering student here at the New Albany Purdue Polytechnic, and today we will be discussing biomimetic architecture. The specific instance of biomimetic architecture that this podcast will be centered around today is a shopping center and office block located in Harare, Zimbabwe. The shopping center is known as Eastgate Center and was designed by McPierce, who's a Zimbabwean architect that is well known because of this revolutionary design. This podcast is going to explain first how the building works, prove that the building does provide self-regulating temperatures due to no more than just the design of the building and fans. Also, the pros and cons of this technology, and really explore why this technology could be so revolutionary. Before we get started with the actual body of this podcast, we first need to define what is biomimetic architecture. And the definition of biomimetic architecture means a building design that has been derived from nature. The Eastgate Center is a primary example of biomimetic architecture because McPierce, the designer of the building, received inspiration from mounds built by fungus farming termites he saw on a nature show. Insects created their own air conditioning system that circulated hot and cool air between the mound and the outside. And similarly, Eastgate copied this kind of procedure. Now, after understanding what biomimetic architecture means, let's get into the meat and potatoes of this podcast by explaining how this technology works in both the day and night to fulfill its purpose of regulating the temperature. So first, how does this work during the day? So along the ridges of the Eastgate Center's roof, there are 48 brick funnels topping internal stacks which pull the exhaust air out of 7 floors of offices below. Under each office floor is a mezzanine plant room, or a floor between ground floor and the first floor of the building. Inside of this room, a chevron screen filters the air for 32 banks of low and high volume fans. The job of the fans is to draw air from the atrium, or an open-roofed entrance hall or central court, through these chevron filters. The air from the atrium is cool air, and its purpose is to cool all the rooms of the building. The air from the atrium is pushed up through a supply section of vertical passageways, which are directed into a central spine, similar to like the central spine of the body of the human body, which can be found in the center of each office wing. Several smaller channels are built into this central supply of cool air, kind of like nerves are in our body, which allow the cool air to regulate the temperature of each individual room in the building. These channels are found in the hollow floors of each room and direct the air through low-level grills underneath each window into a room, and this allows the cool air to disperse all throughout the room. As the air is warmed by human activity, it rises to the top of each room and escapes into another central spine, similar to the atrium as described earlier. The air travels upward and enters into a vaulted ceiling room, which is a room that has a ceiling that angles up toward the roof to extend higher than the standard 8 to 10 foot height of average flat ceilings. And this vaulted ceiling is located at the top of each building. This hot air is sucked out via the exhaust ports at the end of the vaulted ceiling through a system of stonework passageways that direct the air to central vertical stacks that finally release the air back into the atmosphere. The sandwich of a vaulted ceiling and these holes in this vaulted ceiling help act together as a heat exchanger. So now let's find out what happens during the night in order to complete this process and to properly regulate because both the day and the night, the building serves two different purposes. For, usually throughout the day it is much hotter, but during the night it is much cooler temperatures. But both are utilized to complete this process of regulating temperature, and both are essential to completing this process. So let's dig into it. So the void that is located in the vaulted ceiling contains concrete teeth, which allows cold night air to pass through this hole, which removes the heat of the previous day at the same time of cooling the concrete teeth. On the following day, warm external air is cooled by about 3 degrees Celsius as it passes over these same concrete teeth before entering the upper chamber here, and then filters throughout to the rest of the building. So some other piece of technology that are very key to understanding how this process works is both fans and data collection devices. So first, to start with the fans, high volume fans run at night to give 10 air changes per hour, and low volume fans run during the day, giving 2 air changes per hour. By timing the changeover from low to high air velocities, the optimum use of the diurnal swing, meaning the difference between the highest and lowest temperatures in one day, of the biosphere can be utilized. Now on to the data collection devices. So the engineers that have designed this building and that run this building, upkeep it, they've installed data collecting devices in the 5 critical positions to record the air temperature continuously to ensure the infrastructure is performing its job of cooling. After learning about how this building functions, I bet you're left wondering, does this building really live up to the hype of regulating the temperature of basically a skyscraper in an environment that is similar to the hot weather of Texas in the summertime? Well, according to the data loggers, which have been recording the outside air temperature, concrete structural temperature, and temperature of various rooms within the building since 1996, suggest that the building's natural HVAC system is performing quite excellent. A graph was created with the data loggers' information that revealed that under average weather conditions covering a span of 10 months of the year, 37.4 degrees Fahrenheit of cooling between outside and inside temperature is achieved. This proves that the Eastgate's natural HVAC system is just as successful as a standard HVAC system. Now let's explore the pros and cons to this infrastructure. The primary pros of the Eastgate Center is a initial decrease in the building cost and prevents the use of deadly refrigerants. On the other hand, the most significant con is the Eastgate was designed for only one particular climate, and no evidence suggests it could be implemented across other climates. So let's talk about the pros. So how does the Eastgate Center decrease initial building cost and eliminate HVAC systems? Well, according to MikePierce.com, since the building can self-regulate its temperature via how I talked about it previously in the podcast through fans and different chambers within the building, then 10% of the total building cost is eliminated because no HVAC system has to be implemented. Another good website to pull data from, with the name of thepinnacleist.com, states that the average cost of a new HVAC system can cost anywhere from $6,000 to $12,000 for 1,000 square feet of a building. So in the end, the initial cost of a building can be cut down due to no HVAC system, which could help save the company not only millions in the beginning, but also over time as this HVAC system drive up electricity bills and other bills. So now, how does the Eastgate Center prevent the use of deadly refrigerants? According to AskNature.org, AskNature.org explains the impact of the HVAC systems on the environment, and it helps tie into why Eastgate Center is so popular. So it states that the modern refrigerant was first introduced in the 1930s. It was called chlorofluorocarbons, better known as Freon. So this chemical basically escapes into the atmosphere and causes an ozone rip, which is why in 1987 a global agreement was reached to ban the production of CFCs, which actually did cause a ozone layer rip that occurs in October over Antarctica every year now. And the chemicals that actually replace this freon is about just as deadly and still does cause global warming a whole lot faster than any kind of carbon burning fuel process. So the Eastgate Center would eliminate this issue completely by not having the use of HVAC systems. So now let's finish it up with the cons. So Mick Pierce, when he was designing this building, made the assumption that Eastgate Center's design, for it to be successful, only needed to satisfy the weather conditions in Harare, Zimbabwe. I actually discovered this assumption via a paper written by Holly Jacobson called Nature, Biological Templates for Adapting to Climate Change, which states, knowing that Harare's climate was tropical with an 8-month dry season with cool nights and hot days, the client suggested using passive ventilation. This statement exhibits that McPierce accepted a passive ventilation as an answer because of the climate of Harare, which proves he did not design Eastgate for other climates. In today's podcast, I covered how a termite mound inspired a brilliant architect to design a self-cooling building, how the infrastructure works, the pros and cons of the building, and shared my thoughts on the design. I want to wrap up this podcast by sharing just a few things. First, the world should understand that the course that we have set it on will eventually have a detrimental effect on the earth for years to come. Implementing technologies like the one described in the podcast will help extend the longevity of Earth's lifespan by eliminating the production of HVAC systems, which end up in ever-expanding landfills, and it eliminates the production of deadly refrigerants that slowly decompose our precious atmosphere. I want to leave the audience with this. I found this quote on Google, but I figured it really pertained to the conversation. And it came from Wangari Maathai, and he states, "You cannot protect the environment unless you empower people. You inform them, and you help them understand that these resources are their own, and that they must protect them." Thanks for listening. I am Griffin Packwood. Remember, one of our primary goals as human beings is to leave the world a better place for the future generations to come. Thank you.